This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
When we model quantum dynamics, we default to visualizing a quantum wave packet evolving across a perfectly smooth, unbroken space. This assumption dates back to the origin of the framework. Erwin Schrödinger provided the wave equations that define how these states evolve over time. David Hilbert provided the mathematical space. We rely on operators acting on continuous Hilbert spaces to calculate exact physical outcomes. This framework is mathematically bound to its geometry. Standard quantum field theory defines its operations exclusively on perfectly continuous Euclidean manifolds. The canonical quantum toolkit we use today was engineered for an idealized geometry that does not universally exist in nature. Physical reality is built on irregular substrates, porous materials, disordered graphs, and fractal metamaterials. On these fractured metrics, the standard models break. The continuous spatial Laplacian, the mathematical engine of classical quantum mechanics, assumes an unbroken surface. When forced to operate on a recursive or fragmented graph, it fails to compute accurate dynamics. The physical consequence is that wave transport freezes. Instead of expanding symmetrically, the wave packet spreading becomes severely subballistic and chaotic. Standard Euclidean asymptotic scaling is mathematically incapable of mapping the specific type of broken transport. This requires a rigorous reformulation. Fractal Quantum Mechanics, or FQM, rebuilds quantum dynamics natively for these metric measure spaces. FQM achieves this through a specific geometric intervention. It discards the standard spatial dimension entirely, replacing it with a new control parameter, the spectral dimension. This transition is a strict requirement for calculating actual wave transport inside real-world complex media. To build this theory, the continuous spatial Laplacian is removed and replaced by a fractal Dirichlet form operator. The classical action functional changes with it. The standard velocity squared term is crossed out, replaced by the Dirichlet energy form to account for the geometry's resistance. Because the space is no longer smooth, the path integral measure can no longer use standard geometric distance. It is now induced entirely by fractal diffusion and heat kernels. The spectral dimension takes over the entire calculation. It calculates the exact way a wave diffuses through the localized fractal space, assuming the mathematical role usually reserved for standard spacetime. This chart compares the density of quantum states. The continuous curve relies on Euclidean dimensions. The FQM density of states is governed strictly by the spectral dimension equation highlighted here. Because fractal substrates possess discrete scale invariance, a log periodic oscillatory modulation is forced onto the spectrum. This specific rippling signature acts as a clear diagnostic marker. If you observe these oscillations, you are looking at a true FQM system, not a smooth quantum field. On a recursive substrate, the system scaling and field criticality are dictated entirely by the spectral dimension. A functional physical theory must also account for multiple interacting particles. The rules of algebraic symmetrization, the constraints governing bosons and fermions, remain mathematically valid even when the underlying smooth geometry is lost. However, the physical reality of those particles shifts. Their available mode density and their capacity to localize are now filtered by the irregular substrate. When we map multiple particles onto a recursive geometry, the collision diagonal, the mathematical space where particles interact, shrinks and alters its capacity. The substrate's effective measure and energy form redefine exactly how particles experience coincidence and short-range interactions. As we calculate second quantization in FQM, we find the vacuum state is no longer an empty baseline. It is a substrate-filtered spectral measure, inheriting the irregular spectral density of the geometry itself. While the particles remain algebraically indistinguishable, their environment is no longer a uniform void. The vacuum itself becomes a structured physical baseline for a new type of field theory. Tracking how fields interact across these restructured spaces requires defining a two-point correlator. This is difficult in a space that lacks smooth translational invariance. The standard Feynman propagator is discarded, replaced by a substrate-filtered spectral object. The short-distance singularity structures, which were previously dictated by standard spacetime, are now controlled exclusively by the spectral dimension. This introduces the phenomenon of scale-sector coupling. Fields on a fractal substrate propagate not just across physical distance, but across distinct geometric scales. We map this using a matrix grid known as the block-structured propagator. Illuminated diagonal blocks represent standard wave propagation within the same scale. The off-diagonal blocks track cross-scale tunneling. We see exactly which resonant channels allow fields to propagate across scales and which are blocked. FQM correlators map a precise network of scale tunneling. Wave propagation becomes a process of rigorous geometric filtering. A mathematical framework without strict falsifiability is mathematical fiction, not physics. We can isolate speculative extensions in a structural breakdown. To execute a proper collapse analysis, we formally detach unproven claims, like emergent gravity and not topology. This isolates the scientifically grounded minimal viable FQM, the rigorously provable core, and its field theory derivation. This is the survival theorem. FQM maintains its standing as a physical science only if it adheres to this rigorously provable core. This requires an empirical bridge. We must define the exact phenomenological predictions required for laboratory validation. The first mandatory prediction is the experimental observation of a non-classical density of state scaling, driven explicitly by the spectral dimension. The second is the physical detection of log-periodic spectral corrections within discrete substrates. The third is measuring anomalous sub-ballistic transport exponents that deviate from standard integer values. We test these predictions not by searching for fundamental quantum gravity, but by utilizing highly controlled analog experimental platforms. They include recursive photonic lattices, hierarchical electrical circuits, and cold atom synthetic graphs. Fractal Quantum Mechanics provides the mathematical framework to quantize irregular geometries. To cement its reality, the next generation of experimental physics must physically measure the structure of the recursive vacuum.